When we multiply radicals, we want to make sure that we have the same index for both of the radicals in the product. In this case, our index is 3. We are finding the cube root of the two expressions, so we're good in that regard. Normally, when we have to do this, it is out of necessity, because the cube root, it cannot be used to simplify either one of the two factors. So the cube root can't really be used to simplify 4x squared, and while it could be used to simplify the x to the 5th, it really can't be used on the 14. So we want to make sure that we get all of the possible factors out of the product. In order to do that, we begin by multiplying the two radicands of the expressions. So we're going to leave everything inside of the cube root, and we're going to multiply these inside parts of each radical. 4 times 14 is 56. X squared and x to the 5th is x to the 7th. Just as we always would, we could write out the factors of 56 and look for those groups of 3 like we discussed earlier in the lesson. Or, because 56 is a relatively small number, we could think to ourselves, are there any perfect cubes that we know, other than 1, that go into 56? And there is. We can imagine splitting the 56 into 8 and 7. Taking the cube root of that 8 leaves us with a 2 on the outside of the expression. We can't do anything with the 7, so we know it's going to stay inside of the cube root. Now we handle our x to the 7th with the cube root. So x to the 7th to the 1/3 power is x to the 7/3, which is x to the x to the 2 1/3, which leaves us with x squared out here and 1x left over. So there's our simplified version for that expression. Similar to that example, here we have a 4th root. We're going to again start by multiplying everything that's in each of the radicands. So 9 times 9 is 81. We have an x squared and an x to the 4th, which is x to the 6th. We have y cubed and y to the 1st. Remember, if there's no power, there's a 1. So it's y to the 4th. And z squared and z to the 6th is z to the 8th. And we walk through each of those terms. Again, 81, we could write out all of the prime factorization of 81. Or we could say, is there a perfect cube? Or excuse me, in this case, a 4th power that goes into 81. And in fact, 81 is a 4th power. It is the 4th power of 3. So we're going to start by taking that 4th power of 81. Then we'll move on to the 4th power of x to the 6th, which leaves me with an x on the outside. Then we're going to do the 4th root of y to the 4th, which leaves me with a y on the outside. And the 4th root of z to the 8th, which is z to the 2nd. And still on the inside is those last couple of leftover x's. So we see that that 4th root is going to apply to each one of the variables individually. We can imagine splitting it back up and doing them all separately. But because this number is not a multiple of 4, we're left with a couple of x's still inside of the radical. In our last example, we have an entire binomial that's inside of the expression. Now this root is lower than that power, which means that we could do some simplifying there. But keeping with the same trend, it makes sense to continue with multiplying the inside. So we're going to add in an extra factor of x plus 4, which gives me 8 of them, and then working the simplification off of that. So despite the fact that there was something to be done here, we're going to stay with that tradition of multiplying those radicands. I take the 6th root of an 8th power, which leaves me with an x plus 4, and the 2 leftover x plus 4s. So you saw in all 3 of these examples the exact same thing. We have 2 separate factors that were being multiplied together. We had 2 separate radicals that were being multiplied together. We combine their radicands, and we simplify from there.